Good morning, everyone. It's a great honor to be invited to give a talk at this workshop. In this presentation, I will introduce new technologies that can be and have already been used in engineering applications to diagnose, analyze, and reduce various complex noise problems. In particular, I will discuss our latest breakthrough on targeted noise control. There are many challenges in noise control in practice. Basically, we need to address 5W 1H questions, namely, what are the noise sources' sound pressure level, not at measurement locations, but at source locations? Where are the noise sources? When does noise occur? What are their characteristics? Who are they, namely, structure-borne or airborne? Why do they occur? Moreover, we had to face the reality that test environment is never ideal. There are unknown background noise and interference signals, including sound reflections and reverberations. Here we will introduce new technologies that will enable us to identify all vibroacoustic quantities, including source location, source sound pressure level and distribution, source sound intensity and distribution, source strengths and ranking, source radiation pattern in 3D space, normal surface velocity distribution or ODS, correlations between structural vibration and acoustic radiation. These characteristics will enable us to determine the optimal noise reduction strategy. The approach we take is to use sound viewer technologies, whose principles include the passive soda, sonic detection and ranging, the Helmholtz equation least squares method, and FVAC, forced vibroacoustic components analysis. The hardware for sound viewer is very simple. It includes a 3D array of 6 microphones, a miniature wide-angle camera, an 8-channel simultaneous digital signal processor, and a laptop computer. Here is a summary of functionalities of sound viewer versus other technologies for diagnosing and analyzing noise sources. Detailed literature reviews are omitted here for brevity. As you can see, sound viewer technologies have many advantages over the competing technologies in terms of being non-invasive, easy to use, suitable for transient and flow-induced noise, wide frequency range, large dynamic range, high spatial resolution, offering all vibroacoustic quantities on the source surface and in 3D space, capable of extracting target information in the presence of background noise, etc. Now we briefly discuss passive soda. Detailed derivations and experimental validations can be found in references 1 to 3. One can view soda as a radar, except it is passive and utilizes sound waves to locate multiple sound sources simultaneously in 3D space. The basic relationship between sensors and a target source is given by equation 1, where R sub I and J represent respectively the distances between any source and the ith and jth microphone. Delta Tij is the time difference of arrival for a sound signal to travel from the ith to jth microphones. C is the speed of sound, and J is the total number of microphones. Equation 2 is the same formulation expressed under Cartesian coordinates. The explicit solution for the source location XYZ can be found in references 1 to 3, which is very long and therefore omitted here for brevity. Equations 3 and 4 describe the Helmholtz method that seek optimal approximations of the vibroacoustic quantities reconstructed on the source surface and in the field, based on partial input data of the acoustic pressure and normal surface velocity. These formulations can be very handy because in practice it is impossible to collect complete sets of input data at desired locations. The pressure to velocity transfer function is given by equation 5. Similarly, the velocity to velocity transfer function is given by equation 6, where the pseudo-inversion is given by equation 7. In spherical coordinates, the basis functions can be expressed as the spherical Hankel functions and spherical harmonics of the first kind, respectively, as shown in equation 8. Once the acoustic pressure and normal surface velocity are reconstructed, we can write the time-averaged acoustic intensity as equation 9. Accordingly, the time-averaged acoustic power is given by equation 10. Now let's look at F-VAC analysis. Expressing the reconstructed acoustic pressure in terms of the reconstructed normal surface velocity and substituting it into the time-averaged acoustic power in the far field, we obtain equation 11, where the transfer function that correlates the normal surface velocity to the radiated acoustic pressure is given by equation 12. In deriving this expression, we have made use of equation 13. Physically, the transfer function implies the effectiveness of the acoustic power radiation from an arbitrarily shaped source surface to the surrounding fluid medium, and the normal surface velocity distribution depicts the source strengths. Since not all structural vibrations may produce sound, it is of paramount importance to determine the critical components of structural vibrations that can radiate sound effectively. This is the basic idea of F-VAC analysis. Mathematically, F-VACs can be obtained by applying singular value decomposition to the transfer function, equation 14, where U and V are the left and right unitary matrices respectively, and sigma is a diagonal matrix consisting of the singular values of the transfer function given by equation 15. Now let's see some representative examples of using sound viewer technologies to analyze the complex noise sources, for example, automobile muffler noise. Note that the spatial resolution of sound viewer is independent of the frequency. In other words, sound viewer enables one to pinpoint the source location even at very low frequencies, below 200 Hz. This example shows the capability of sound viewer to eliminate interference signals and extracting four-cylinder engine combustion noise. Here is an example of using sound viewer to diagnose and analyze motorcycle low-frequency rumbling noise. There are several features that need our special attention in this example. First, the frequencies are very low, below 200 Hz. Second, source locations are identified with very high spatial resolutions. Third, source strengths are determined and ranked. And fourth, radiation patterns in 2D and 3D space are determined in terms of dBA values. What I want to show in particular in this presentation is the targeted noise control. The strategy has been applied successfully to the auto industry, for example on a full-size truck front dash panel. However, because of a non-disclosure agreement, I cannot share these results. Therefore, we selected a household appliance, namely a dishwasher, as an example. The point I want to make is that this target noise control is applicable to all structure-borne sound radiation and sound transmission. Here is the test setup for a dishwasher. 4 accelerometers were used to measure the surface acceleration signals on the dishwasher front surface over 6x7 grids. Acoustic pressure signals were measured by a sound viewer at a distance of 90 centimeters. Before applying the targeted noise control strategy, we first validate the vibroacoustic quantities reconstructed by the SoundViewer technologies. Shown here is the comparison of the spatially averaged acoustic pressure spectra measured by an array of microphones and those reconstructed by the SoundViewer software. Satisfactory agreement is obtained in this case. The reason we show the spectrum up to 1000 Hz is because the sound pressure level drops continuously beyond 1000 Hz, which indicates that the dishwasher noise is primarily generated by structure-borne sound. The spectra indicates that there are 4 major resonance peaks at 169 Hz, 248 Hz, 342 Hz, and 557 Hz. These peaks were selected as targeted frequencies in this example. Next, we demonstrate the comparison of the measured normal surface velocity spectrum versus the reconstructed one. Once again, satisfactory agreement is obtained. Note that the amplitudes of the normal surface velocities decay drastically over frequencies, and resonances occur primarily at low frequencies. These results further prove that dishwasher noise is structure-borne. In addition to surface velocity spectrum, we also compare the forced vibration patterns, namely operational deflection shape, ODS, with the reconstructed ones. For brevity, we only displayed validations of the measured ODS versus reconstructed ones at targeted frequencies, namely 169 Hz, 248 Hz, 342 Hz, and 557 Hz. It is emphasized that measured ODS in each resonance frequency was rough because the number of measurement points were not enough. On the other hand, the reconstructed ODS was very smooth, and the amplitude of ODS was accurately preserved. This is one of many unique capabilities of the SoundViewer software that enables one to acquire satisfactory reconstructions based on relatively fewer measurement points. Shown here are the ODS results in 3D space, which provides a direct and easy-to-understand format to visualize the actual structural vibration of a dishwasher at each resonance frequency. This is another unique feature of the SoundViewer software. Shown here are the 3D time-averaged acoustic intensity vector distributions on the front surface of a dishwasher at the corresponding resonance frequencies. These acoustic intensity vectors indicate the flows of the acoustic energies from the dishwasher front surface into the surrounding fluid medium. The main idea of targeted noise control is to identify the most critical components of structural vibrations known as FVAC, which are responsible for sound radiation at targeted frequencies or target frequency bands. The reason why FVAC analysis is important is because, although sound is generated by vibrations, not all vibrations can produce sound. In fact, only a very small portion of structural vibrations can effectively emit sound. Therefore, if our goal is to reduce noise, we should use FVAC analysis, not the model analysis that has nothing to do with sound radiation. Once the most critical components of structural vibrations are identified, we can use viscoelastic patches to suppress vibrations. Viscoelastic patches are typically very thin. For example, Shiloh's acoustic patches are easy to apply and their thickness can be less than 1 mm. Therefore, they will not increase the overall weight of the structure. Note that the overall structure weight can be critically important in the aerospace and automobile industries. Here is the comparison of the original spatially averaged sound pressure spectrum versus that after applying targeted noise control. Results show that the sound pressure levels are reduced across the entire frequency span, not just at the targeted resonance frequencies. It is important to point out that one can combine this targeted noise control strategy with psychoacoustics and explore various design options to meet the noise reduction requirements through numerical simulations. In other words, one can perform design optimization by selecting where and how much to suppress the critical structural vibrations that are responsible for sound radiation in a virtual environment. In conclusion, we can state that targeted noise control strategy works. This strategy is highly effective and covers a wide frequency range, not just the target frequencies or target frequency bands. Second, we can suppress structural vibrations only where they are needed. The key to success is the use of effect analysis that can identify the critical components of structural vibrations that actually radiate sound and leave the rest intact. And third, the outcome of target noise control are quieter and superior products. It is emphasized that this targeted noise control strategy is applicable to all structure-borne sound, including aircraft cabin noise, and automobile or locomotive passenger compartment noise, household appliances noise, etc. Thank you very much for your attention.